two different derivations for the Clausen integral identity. So in the past few weeks, we have been just doing the Clausen integral function. And the Clausen integral function base 2 is the special case of the Clausen function. And this is defined as the sum from k equals to 1 to infinity of sine k theta by k square. Yes? And we have also seen the integral representation for this function, which is over here. Minus integral from 0 to theta of log 2 sine x by 2 dx. And in this video, our sole aim is to prove these two identities. First of all, there are two ways. One of them will be to differentiate this sum, find the sum, and again integrate the sum. And next one will be the use of full logarithm function. Yes, because full logarithm function, if we input e to the power theta in it, we will get an integral representation. This can be simplified as well. And also, if it's e to the power theta, the imaginary part will conjugate sine of theta. So there are two ways to do this. Now let's do. So we know that Clausen integral function is defined as this sum from k equals to 1 to infinity of sine k theta by k square. Yes, and if we differentiate this with respect to theta, we get this following sum. So we just take the derivative inside the sum, and then sum from k equals to 1 to infinity cos k theta by k square. Now again, using chain rule, we need to differentiate k theta, so we get k. Cancels out. Now the reason I differentiated is now this sum, just since it has just like k in denominator and not k square, this sum will somehow be evaluated using logarithm function. So that's why I did this. And to evaluate it by logarithm function, first of all, we need to make an exponential in the numerator, which you can clearly do because cos theta is just the real part of the e to the power theta. Yes, because e to the power theta is just cos theta plus sin theta. So that's why cos theta can be told as the real part of e to the power I k theta d theta by k. Now actually real part of e to the power theta should be here, but since the k is also a real number, so we can again divide this, and again we can take the real part outside of the sum because since all the other things that we are dealing with are real, and this can be done. Okay, now d theta of cl to theta is equals to, now to evaluate this sum, what we can do is first of all write it as an exponent in the exponential form, e to the power I theta to the power k by k. Now this is just x to the power k by k, where we know that there is a logarithm sum for this Taylor series. Yes, and that is minus ln of 1 minus x. So this is just the real part of minus ln of 1 minus e to the power I theta. Yes, yeah. And now after we have this, we can just uh, try to evaluate this logarithm d theta of cl2 of theta. Now we know that, first of all, let me write this in a proper way. So this is just cos theta, sorry. E to the power theta is cos theta plus sin theta, yeah, so it is cos theta and then minus I sin theta. Now please know that whenever we need to find the logarithm of x plus iy, we know that any complex number can be written as g and e to the power I theta, yes, where g is the modulus, theta is the argument, and it can be written in this form. And now after that we know that it's just ln of g plus I theta. Yes, so we see that the real part of a logarithm function is always just the real part. Is always just the logarithm of its magnitude, and its argument will be the imaginary part. So let's just find the real part. Let's find the logarithm of its magnitude. So d theta of Cl2 of theta will just be the logarithm of its magnitude. Magnitude is square root of 1 minus cos theta square plus minus sin theta square. Yes, this is the real part. Now, again, d theta of Cl2 of theta will just be negative of ln of the. Now, this is just 1 minus 2 cos theta plus cos square theta plus sin square theta. Yes, and we know that cos square plus theta plus sin square theta is just 1. So, d theta of Cl2 of theta is equals to minus ln of this is 1, this is 1, so 2 minus 2 cos theta. Okay, good. Now again, d theta of Cl2 of theta will be minus ln of, take 2 as common, and then 1 minus cos theta will be 2 sin square theta by 2. So 2 times 2 sin square theta by 2. Yeah, and after this we have d theta of Cl2 of theta will be minus ln of 2 sin theta by 2. Minus ln of 2 sin theta by 2. Yes. Now, we are almost at the end. Yeah. Now what we can do is we can integrate both sides with respect to theta. If we integrate both sides with respect to theta, if we integrate, first of all, we know that our final answer has theta in the integrand. Yes, over here, and there is x. So first of all, let us write this with respect to x and then integrate with the limit as 0 to theta. Yeah? So d dx of Cl2 of x will be minus ln of 2 sine x by 2. And now let us differentiate this with respect to x and then integrate from 0 to theta, from 0 to theta. Now over here in the first integral we can look at it like dx cancel out and d of something is that just something. So Cl2 of x integral from 0 to theta will be minus of the integral from 0 to theta of ln of 2 sine x by 2 dx. And after this, we know that if we evaluate this at theta, it will just be Cl2 of theta, and at 0, Cl2 of 0 will be just 0 because Cl2 of theta is just the sum of the sines. Yes, Cl2 of, we had seen that Cl2 of k theta is just the sum of sine k theta by k. So if theta is 0, this will just go to 0 for every value of k. Yeah, so Cl2 of 0 is just 0, and over here this is minus integral from 0 to theta of ln of 2 sine x by 2 dx. Yes, and then and so this will just be Cl2 of theta is equals to minus integral from 0 to theta of ln of 2 sine x by 2 dx. So this is our answer. You get this? Yes, probably. And next method is also based on similar principles because while finding the integral for Li2, we just use the integral for log, and that's almost quite similar. The reasoning, the like base reasoning is the same, but yeah, it can look like a different process for most of us. Yeah. So this is one of the proof of this identity. Now let's go to the next one. So we will start with the Li2 of e to the power I theta. Yeah, because we know its integral representation. That one is also derived from basically the log itself. So these are kind of same, but yeah, let me do it. Integral from 0 to e to the power I theta of minus ln of 1 minus x by x dx. Yes. Now, if I take, we know that this is just a sum from k equals to 1 to infinity of e to the power I theta to the power k by k square. Yes, basically if it is x, so x to the power k by k to the power p, where this number is p. Yes, so this is the sum. And now if I take the imaginary part of this sum, what we get is just the sign, just the sign of k theta. So because these two are now going to multiply, to the power I k theta will be there. So we just get sine of k theta by k. So it's the expression over here. Now, now this can be dealt with easily. Now, what we need to do is just to simplify the other part. Now, to simplify this expression, what you can do is, first of all, let us make this 0 as 1. Let me write it as integral from 0 to 1 of minus ln of 1 minus x by x dx plus integral from 1 to infinity 1 to e to the power theta 1 to e to the power I theta of minus ln of 1 minus x by x dx. Okay, good. Now, if I take the imaginary part, okay, I'll do it later on. First of all, let me just multiply the powers. e to the power I k theta by k square is equals. Now we know that this is just minus li2 of 1. Yes, and then plus, because minus ln of 1 minus x by x is just li2 of anything that's over here. Oh, how come I get the minus n over there? It's not minus. Sorry. Okay. We know that this is because the integral of minus 7 of 1 minus x by x dx, if let's say here is alpha, that is just li2 of alpha. So it's 1, so li2 of 1. And we know that from the sum, like expression, li2 of 1 will just be 1 by t square. So that's just it after actually. Now, over here, to simplify this, I can make the limits go from 0 to 1 if I say that theta is ln of x. Now guys know that this is e to the power theta. Right? So I'm trying to make it go from 0 to 0 to like I'm trying to make it go from 0 to x. Right? If I take first ln of x, this will just be I theta. Now divided by I. Okay, now if I do this, this will just be theta and this will just be 0. Right? Yes. So theta is ln of x by I. That implies x is just e to the power theta. You know that now. So if I make this substitution, let me put the substitution a bit in the side because here I need to make the solution. Okay, if I make this substitution, we know that this is going to be integral from 0 to theta of minus ln of now. But is this going to be from 0 to theta? Hmm. Okay, so theta is ln of x by I. So theta is oh, hold on a second. So this was our I to the power I theta cancel theta. No. Wait. So I'm basically saying that x is e to the power I theta. So this should be our x. Yes, How come I need to get this intuition from this expression? Hmm. Okay, so e to the power is x, so let me write x over here, and this will just be 0 from the other expression. Oh, good. Now, now up to this, we know that now this will just be minus ln of 1 minus x is e to the power I theta by x is e to the power I theta, and dx is equals to I e to the power I theta d theta. Yes. Now the limits are simplified, so it will be easier to solve. Yes. And also the buy one get one free offer is that this to cancel out. Okay. Now if I take the imaginary part, actually I can also take imaginary part inside the integral. So this will just simplify further. And that pretty much solves the problem in the way how we solved it earlier. Yes. Now if I take the imaginary part of this expression, this will be just sum from k equals to 1 to infinity of sine k theta by k square. Yes. And now this is just a real thing, so it will not be counted. Now over here, there is I over here. So let me return that I as it is. And from this expression, we will just count whatever is imaginary. Yes. But now let me just first of all evaluate. And now we know that ln of, okay. Okay. So what I can do is, since we know that there is an I over here, if we find the real part from this other expression, then the whole thing will be the imaginary part. Yes. So that's why I basically need to find the real part from this expression. And we have already done that in the previous solution as well. The real part of this expression is just minus ln of 2 sine theta by 2. Yes. Now again, how come this is messed up? Okay, the problem I think is I should have let this. The problem was, yeah, the way I wrote x over here was the problem because now the variables are not matching. So I should not use the same variable. I can just use y. Then it will be different variable, and now it should work. Okay, yeah. Well, let me go with that flow. If I use y, then x is equals to e to the power iy. Yes. Now over here it will just be then now it will just be theta. Now over here it will be e to the power iy, e to the power iy, e to the power iy dy. Okay, now only it works, and now there is no confusion. Why? 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 And now this is also a run of sign. Okay, now it makes sense to me. Dy, good. And this is also y. Okay, now this is theta. This is theta. Now it makes perfect sense. Now this answer will be in terms of theta, and this is also in terms of theta. And now we know that this is just the Clausen integral function of yes, because this is the sine k theta by k square, which we have already defined. And now this is our required integral integral from 0 to theta of minus ln of, okay, I have already written minus integral from 0 to theta, and then ln of, I can also write this as x and not y, 2 sine x by 2 dx. So we have proved this using both the ways. Yes, from logarithm integral function or from just logarithm. Both of them are in fact similar because we have come across similar ideas. Just that it was a bit shorter to look at because we have already done these things over here. So that was it. Hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the upcoming videos, and I'm sorry for being inactive for some time.